Hello, this is lesson 7, where we will talk about symmetry. So first, we can just look at some pictures to discuss symmetry, and then we will use equations. So there's 3 types of symmetry we will talk about. Symmetric, about the x-axis, symmetric, about the y-axis, and symmetric about the origin. Okay. So if we look at x-axis symmetry first, that's when the x-axis is sort of acting like a mirror. So say we have a graph of some relation. I'll do it in red. Notice how this graph in red is symmetric about the x-axis in the way that the x-axis is acting like a mirror, or this portion of the graph is the mirror image of this portion, provided that the x-axis is the mirror. So that's what we mean by x-axis symmetry. Everything over here reflected about the x-axis has its mirror image on the graph. So let me draw a few pictures of x-axis symmetric relations or functions here. So, you could just draw something, and as long as its mirror image is flipped about the x-axis, this would be symmetric about the x-axis. So these are all examples of symmetric about the x-axis. Now if we look at things that are symmetric about the y-axis, as you may have guessed, it's the same thing, but just now the y-axis is acting like a mirror. So if we have the x and y axis here, say we have some graph, then its mirror image is going to be flipped about the y-axis here. So notice the y-axis that I drew here in yellow is acting like the mirror. Everything on the graph here is the mirror image of everything over here. So let me graph a few more examples of y-symmetric things. We could have something like this, and then its mirror image. So these are not perfect pictures, but imagine they're perfect mirror images of each other about the y-axis. Things like this. Okay, so this is y symmetry. And then there was the third one I mentioned, when it is symmetric about the origin. Now remember, the origin is just this point in the middle, the point 0, 0. Right, that is the origin. So if something's symmetric about the origin, that means the origin is acting like a mirror. So if we have something like that, we reflect it about the origin, its mirror image would be, over there, like that. So whenever you see a graph and this point in the middle is acting like the mirror, then we have origin symmetry. So I'll try to graph a few examples here. These are symmetric about the origin. Okay, now that we've seen what the graphs look like, let's look at the equation part of symmetry. So we could start with X symmetry. So notice when we have something symmetric about the x-axis, that means say we'll have a point here on the graph and then a corresponding point here. So that'd be some x value. Let's say that's when x equals a. And here, let's say y equals b. So this point here on the graph is a, b. Well, then this point here would be a minus b. So that's sort of the picture we have with x-axis symmetry. For any x value, we have this corresponding y value and also this corresponding y value, where it's the same value, but one is positive, the other is negative. So to test an equation for x-axis symmetry, all we have to do is replace the y with a minus y, and if this produces an equivalent equation, then we have x-axis symmetry. Equivalent equation. Then the equation is symmetric about the x-axis. So for example, if we're dealing with something like x equals y squared minus 1, if we want to test this for x-axis symmetry, we replace the y with a minus y. And then we see if this is equivalent to the original equation or not. Well, negative squared will actually cancel out, so this actually is the same thing as positive y squared minus 1. And that is the same thing as the original equation, so this, in fact, is symmetric about the x-axis. Okay, let's look at symmetry about the y-axis. We have a function symmetric about the y-axis. For some point y value here, let's say we have b. Let's say the x coordinate is a. So for this point AB on the graph, notice b will also correspond to another point on the graph. We have this point here. And for this to be symmetric, this value will have to be minus a. So for a y value, we will have two corresponding x values, and they'll be the same value but opposite sign, a plus sign or a minus sign in front. So to test for y symmetry in an equation, we just simply replace the x with a minus x, and we simplify And if this produces an equivalent equation to the original equation, and the original equation is symmetric about the y-axis. So for example, say we have y equals 3x squared plus 1. If we were to replace the x in this equation with a minus x, we get y equals 3 minus x squared plus 1. And then we simplify, well, the minus squared cancels out. So we end up with the same thing as the original equation. So this checks out. This is in fact symmetric about the y-axis. Okay, the last type of symmetry we wanted to talk about was origin. If we draw a picture here to help us come up with a test, let's look at a function like this. So if we pick a point on the graph, a point AB, for this to be symmetric, we would also need a point to be here, and this point would have to be given by minus A minus B. So here we have to replace x with a minus x. We have to replace y with a minus y, minus y. And if we get the, and if this produces the original, if this produces the original equation we started with, then we have origin symmetry. So this produces the same equation that we started with. It is symmetric about the origin. So let me do an example. We have y equals x cubed. Let's now replace the y with a minus y. We'll replace the x with a minus x. Okay, so we have negative y, and then negative 1 cubed is still negative 1, so we end up with a minus sign out front. And now we could just multiply both sides by negative 1 and cancel out those negative signs. And we end up with the same equation we started with. So we replace the y with minus y, replace the x with minus x, and it produced the original equation. So therefore this is symmetric about the origin. For the three types of symmetry. Let me just make a remark. Not everything is symmetric. So say we were dealing with a function like this. This one has no symmetry, right? No symmetry. So sometimes you may test for a function and it doesn't pass any of the tests, and that's okay. Not everything has to be symmetric, but so that was just a remark I made. Let me give an example. Say we have a function like, I don't know, y equals x to the fourth plus x cubed. Now if we test this for symmetry, it will fail all the tests, right? If we test it for, let's say we do the x-axis symmetry, so that was when we replaced the y with a minus y. Let's see if it gives us back the original equation. So if we do a minus y there, right? There's nothing else we can do to simplify this, so there's no way to get back to the original equation when we switched the y with a minus y. So it failed that test. If we do the other test where we replace the x with a minus x, okay, well, the minus x will cancel out here, but the minus x does not cancel out here. Minus 1 cubed equals minus 1. So this simplifies to y equals positive x to the fourth minus x cubed. And there's no way to get this back to the original equation, so it failed the test for y symmetry. And then if we tested this equation for origin symmetry, we'd replace the y with a minus y, replace the x with a minus x, simplify, so we get this. Could multiply both sides by -1. We get this, which is not the original equation. So this function failed all 3 tests. So it has no symmetry. It's not symmetric about y, x, or the origin. So that's the 4 cases you will see. You'll either see symmetric about y, symmetric about x, symmetric about origin, which looks like this, or no symmetry. And that concludes our discussion about symmetry. Thank you.